my name is Dan Oake and I'm a student at Athabasca University, and I'm currently taking the course COM 444, Embedded Robotic Programming. And if you've been following the videos that I've been posting on the course forum so far, you'll know that I'm going through the SparkFun Inventor's Kit guide. This guide is associated with the SparkFun Inventor's Kit, which came with your registration into the COM 444 course. This kit comes with a generic Arduino compatible microcontroller, specifically the RedBoard by SparkFun Electronics, a breadboard, and a lot of other components, some actuators and sensors, so that you can make lots of fun projects, including Project 2, which is what our focus will be on today. In the previous videos, we did Project 1, which incorporated 4 different circuits. Today we're going to be working on Project 2, which is 3 circuits. And I've created a summary to help keep me on track. So, if you're going to watch today's video, this is what you'll see. We're going to discuss Project 2 of the SparkFun Inventor's Kit guide, which focuses on sound. We'll cover 3 circuits and key coding concepts related to producing sounds using Arduino. So, the different circuits that we're going to be working on are highlighted in the different colors from yellow, red, and blue. So, Circuit 2A, buzzer, introduces the basics of sound generation. So I'll explain how the piezo buzzer works, including the difference between passive and active buzzers, and show you how to connect the buzzer to a digital pin. In the code, we'll use the tone to produce different frequencies and looping sounds within the loop function. And upcoming adjustments and experimenting with frequency will be part of the coding challenge for the circuit. So for the project today, I'm going to show you the basic circuit associated with the project, the 3 basic circuits, as well as I've completed the coding challenges for the Project 2 as well. So we'll be going through those. The second circuit, Circuit 2B, is a digital trumpet. It builds on the previous circuit by using multiple buzzes and buttons to create melodies. Here I'll discuss the use of arrays to store musical notes and how to implement tone in combination with for loops for playing melodies. The coding challenge involves programming a short tune of your own, which showcases creativity and understanding of sound generation further. Moving on to Circuit 2C, Simon Says game, I'll explain how we incorporate multiple buttons to create an interactive game. This circuit uses buzzers and LEDs for feedback based on user input. I'll describe how to read inputs with digitalRead and use conditionals, so if-else statements, to determine if the user's guess is correct or not. The game logic implementation and arrays will provide insight into handling sequences and user interactions, culminating in the coding challenge where players can change the game pattern to add complexity. Throughout the video, I'll stress good coding practices, mention some debugging tips, and how to modify the original code provided by SparkFun Inventor's Kit website for customization, so you can it'll help you with the coding challenges. And this should ensure a well-rounded understanding of sound-based projects. So I've created notes for each of the different circuits, but first let's go to the SparkFun guide and go right to Project 2. So, Project 2. In Project 2, you will venture into the world of buttons and buzzers while building your own Simon Says game. That's the third circuit. Simon Says is a game in which the LEDs flash a pattern of red, green, yellow, and blue blinks, and the user must recreate the pattern using color-coded buttons before the timer runs out. So I'm 40 years old, so anyone my age would have known growing up the very popular Simon Says game. And that game has still been around. My kids have played it. I actually went to Activate the other day, and there's a version of that at Activate, which is like an indoor rec place for anyone who's not familiar. So it's still a very popular game. So if you're watching my previous videos, I'm not going to read everything. I'm just going to pick up the main highlights here. So for Circuit 2A, buzzer, it basically incorporates a small buzzer to make music. So you'll see the buzzer here in my circuit here. It's just a small piezoelectric buzzer, and that's what it looks like. So the components you'll need is a potentiometer, a buzzer, and 4 jumper wires. So the new components you're going to learn about today are first the buzzer, and again the buzzer just uses a small magnetic coil to vibrate a metal disc. And so pulsing this electricity through the coil at different rates creates different frequencies or pitches of sound. And we're also going to attach a potentiometer to the output, which is going to allow us to limit the amount of current moving through the buzzer and lower its volume. So again, the potentiometer is not required. You can hook up the speaker without a potentiometer. The potentiometer is just going to allow us to control that volume. We're also going to have a new concept such as the reset button. So on the microcontroller, the RedBoard or any generic Arduino microcontroller, you're going to have a reset button. So there's the reset button right there. And that basically just resets the code. So it starts your program over. Because again, the way Arduino works is you get stuck in this endless loop after you went through your setup loop. So again, the reset button on the RedBoard or any generic Arduino controller is a reset button that will start the code over from the beginning, running setup and loop again. We're also going to discuss the tone function, and the tone function is used to control the buzzer. So you'll use the tone function, which is similar to Pulse Width Modulation, PWM, in that it generates a wave that is of a certain frequency on the specified pin. And that's how Pulse Width Modulation works. If you remember, we have certain digital pins on the RedBoard or any generic Arduino board that have these little tilde symbols next to it, namely 3, 5, 6, and 9, 10, 11. They have this little tilde symbol next to them. And that means that you can do more than just send a pulse of high or low to the board, a digital write, where you're sending either 0 volts or 5 volts to the output. You can send anywhere from 0 to 5 volts with a resolution of 0 to 255. So you can send 256 different levels of voltage to a pulse width modulation pin. So the tone kind of works similarly in that we can send different frequencies, but it doesn't have to be a pulse width modulation pin. So the frequency and duration can both be passed to the tone function when calling it. So you can pass the frequency that you want to emit as well as how long you want to emit that. The duration is optional. So to turn the tone off, you need to call the no tone function, aptly named, or you can pass a duration of time for it to play and then stop. So again, there's an option. You can call the tone function passing in a single parameter, which is the frequency that you want to output, and then call the no tone function after a certain delay of time that you call. So you'd call the tone function passing in a parameter of whatever frequency you want to play, then call the delay function in your code for a certain number of milliseconds, and then call the no tone function to stop the frequency. Or alternatively, you could call the tone function originally passing in 2 parameters, the first one being the frequency that you wish to emit on the piezoelectric buzzer, and the second parameter being the duration in milliseconds that you wish to play the tone for, and then it'll stop after that time, in which case you don't have to use the no tone. Unlike pulse width modulation, tone can be used on any digital pin. So I mentioned that just a second ago. The pulse width modulation, there's only the certain pins on the Arduino boards that'll do that, namely 3, 5, 6, 9, 10, and 11. So you have the 6 pulse width modulation pins out of the 14 digital pins. However, any digital pin, you can use the tone function. We're also going to discuss arrays, which are used like variables, but they can store multiple values. So the simplest array is just a list. So it's, again, just a list of variables. So, and if you want to refer to a specific value within the array, you have to use the index number, which, and as computer scientists, we always count from 0 because arrays are indexed from 0. So this is how you would access it. You'd go whatever the array name is, sub 0, to access the first element, and you'd use, whatever the array name is, sub 1, to access the second element, and so on. This will be important for the code going forward. We're going to be dealing with musical notes A through G. The musical notes have these corresponding frequencies. So musical note A has frequency 220 hertz, and G has a frequency of 390 hertz. We can use variables to describe those by just creating some constant, A sub frequency, and all the way through G sub frequency. Or alternatively, we could use an array and just go frequency sub 0, accessing the element that we store as the first element within our array, which would be our musical note A with a frequency of 220. So both these ways of doing things, using variables and using arrays, will be shown in the code. Okay, so basically you're going to go through the guide and just use the schematics, the circuit diagrams, as well as the connection type information here to set up your breadboard and your connection as normal. But I'll just go through a couple of things. So if we're hooking up a potentiometer to the speaker, we don't need to. We could just have one end of the speaker hooked to ground and the other end hooked to the pin that we're going to be outputting a tone through. That's all we have to do, but because we want to have volume control, we send it through a potentiometer. We're not using the potentiometer in the regular way. You'll remember in a previous circuit, both of the terminal leads on the potentiometer, meaning that both of the outside leads, one was connected to 5 volts, one was connected to ground. Okay, and the middle, which is the wiper, was the one that we connected to one of our analog inputs and read that. We would adjust the knob and we would read something different on our analog input. So the middle pin was the wiper, and that was where we were that was the voltage divider essentially of the potentiometer, because a potentiometer is really just a variable resistor. In this case, we're using it a little differently. We have the positive lead denoted by this little positive symbol, and you can see it on the underside of the circuit as well, the little positive sign. The positive lead is connected to one of our digital pins that we're going to be sending the tone function through. And the negative lead, instead of going directly to ground, we're going to go through one of the terminals, one of the exterior terminals of the pot, and then come through the wiper to ground. And so we're using the potentiometer a little different here, but this will allow us to essentially do that, control the amount of resistance that we go through, which is going to allow us to have a volume control. So again, volume knob, we are only going to use 2 of the potentiometer's legs. So in this case, the potentiometer is going to be acting as a variable resistor, therefore limiting the amount of current flowing to the speaker and thus affecting the volume. Because again, if we allow the full 5 volts of current to go to the speaker, it'll be loud. If we limit that current, we will have, it'll be less loud. If we limit it all the way to 0, it would be muted. But anywhere in between 0 and 5 volts, meaning if we have the knob turned to either extreme, anywhere in between there we'll have some volume, but it'll be varied. Again, keep in mind the speaker is a polarized component, so make sure you do have the positive end connected to your microcontroller digital pin and the negative end going through your potentiometer to ground. And obviously we have the potentiometer connected to the negative rail of the breadboard, which is then connected to ground on our microcontroller. So without further ado, basically let's get to the code. I guess at first I'll do the quick program overview. So that's what your circuit should look like. It should have the speaker, one end of the speaker, this blue wire is presumably going to the digital pin on the microcontroller, and then the negative lead is going through this white wire into one of the terminal ends of the potentiometer, and then the wiper wire is coming back to ground right here, and then this negative ground rail of the breadboard will be connected to the microcontroller. It's ground. So the quick program overview is we're going to play the note for some number of beats using the play function. Inside the play function, we're going to take that note passed to the play function and compare it to each letter in the notes array. And when you find a note that matches, just remember the index of that position of that note, e.g. if it's a 6th entry in the notes array, and then we're going to get the frequency from the frequency array that has the same index as the note that matched the 6th frequency. And then we're going to play the frequency for that number of beats passed by the play function. And then we're just going to play the second note using the play function and so on. We'll come back to the code denote after we actually show the code. So, didn't mean to do that. So this is the code that you'll find. Again, you can, as before with Project 1, you can download all of the code for all of the projects and all of the circuits in the SparkFun Inventors Kit Guide from the website, which is on the first page in the SparkFun Guide. Just go to sparkfun.com or whatever that website is, and you'll be able to download all the code. So the code always starts off with a little multi-line comment of what the code does. In this case, it plays notes using a buzzer connected to pin 10. And as always, they include their circuit diagram. You can click the link to go to the website at sparkfun.com to get the circuit diagram or the code. So I'm going to go through this quick. Anything that's we've done before, they just create a variable for the speaker pins 10, so we can use speaker pin directly in things like our pin mode and be a little more explicit than putting the magic number 10 there, which I like. Although I would prefer if this was a constant. I've mentioned this before. I think it's better to put this as a constant because we don't plan on changing the speaker pin in the code. So make that a constant. And if that was a constant by convention, I would make these uppercase and separating words with an underscore. But this is what this code was in this, so we'll just leave it like that as a variable. Again, in setup, all we're doing is we're calling pin mode and setting speaker pin as an output. And that makes sense because it is a speaker. And then in the loop, all we're doing is calling this play function over and over and over and over, each time passing in two arguments, a character representing the note to play, and the second argument is an integer representing the number of beats, so how long to play. And then we've got a couple pauses in here, which the character is simply a space. So, and then at the end we have a while true loop that doesn't do anything. And this is a very common convention where you just go while true and then just have an empty body for a loop. It just allows you to basically get stuck in the loop forever. It just creates an endless loop, which typically you don't want to do. But in this case, we want the Arduino program just to play the song, in this case, Happy Birthday to You, over and over forever, just to drive someone nuts. So this Arduino is obviously being used at Guantanamo Bay or something like that as a torture. So here's where the actual brains of the code comes in. So this is the play function that they've created. The play function takes in two parameters, one of type char, name note, and one of type int for beats. We also have a variable representing how many notes there are. So this is the variable size, the size of the array rather. So, if we were to count this, it would presumably add up to 14. So this array is used to look up the notes. So we have notes, one-dimensional array called char. So it's a one-dimensional array of type char. And again, it's just used to look up the notes. I'm not really a musical person, so this is all kind of foreign to me, but obviously we have lowercase notes and uppercase notes for some reason. But the important thing here is we have a one-dimensional array of type int called frequencies, and they have the same size. So let me just... So that's really the important thing. I apologize for the size of the font here. I realize that might be hard to see, so let's get it up at least 18. So the important thing to note is these two one-dimensional arrays, even though one is of type char and one is of type int, they have the same number of elements. So when we iterate through, if we're at the fourth element in this array, it corresponds with the fourth element in this array. So we want to play note F for a beat of 175 milliseconds. Then we have a variable for the current frequency, which we're just setting to 0 here, and that's just going to store the current frequency that we're using that we happen to be on, which we'll use later in the code. The beat length is 150 milliseconds. That's just, I guess, what the tempo that sounds good. So again, changing this length will speed up or slow down the tempo. So if we increase this number, we'll slow down the tempo. If we decrease this number, we'll speed it up. And then this is to look up the frequency that corresponds to the note. So we use a for loop to iterate 4 times, not 4 times. So we're going to iterate 13 times, or correction, 14 times, from 0 up to but not including 14. So the way a for loop works is there's three sections of a for loop within the parenthesis. The first one being the initialization, so you initialize some variable, int, in this case I, which is a very common variable used in for loops, int I equals 0, and then you have your conditional statement, which this is the loop will execute the code inside the loop if this condition holds true. So in this case, as long as I is less than num notes, which is 14, we will keep iterating the loop, and this is our update. So after we execute the loop, we will come and do an update of our variable, because if we don't, we will just get stuck forever in an endless for loop. So we update, in this case, I by 1. So in this case, we're going to go from 0 up to, when this is 13, we'll still loop, because 13 less than num notes, yeah. Less than 14 is extra. But when this is 14, we won't. So we'll iterate 14 times, 0 up to 13. Which should take us through this thing. Let's see. Let's verify. That's 5. That's 10. And that's 14, 15. Wait, I might have counted wrong there. That is 5. That is 10. And that is 15. Okay, so I guess we should actually be looping 15 times. We should have a this should be 15. There are 15 values, but arrays start at 0. Okay, so I download this code directly from SparkFun websites. They do have 14 in here. I didn't notice any issues with the code, but this should be 15 because even though they have some note here, number of notes in our note and frequency array, there are 15 values, but arrays start at 0. This still needs to be a 15 because the loop here goes as long as I is less than or equal to num notes, or sorry, less than num notes, meaning it's a strict inequality. So when this is 13, that's the last time we'll iterate. So we'll iterate 0 and then 1 through 13, which is 14 times. But we need to iterate 14 times, or 15 times rather. So this really should be 15. We'll actually leave it for now and see if there's an issue with the code, and then we'll change it live. But let's just verify that that's... Yeah, so that seems to be a mistake, unless I'm not seeing something, but we'll come back to that. Then we're going to look up the frequency that corresponds to the note. So, as I said, we're iterating through this for loop. We're going to check each value in the notes from 0 to 14, although we know we're going to check it from 0 to 13, right, as of now. And we're going to do that by going if note sub I equals note. So this is how we access the individual elements of an array. We go notes, and then in square brackets we put the index number. So this could be 0 or 1 or 2 or 3, and we know we're going through a for loop, so this is going to change from 0 up to 13. And we're going to grab each of those things. And when we grab that, when we compare the element that's at the note array in the notes array at that index, we're going to compare it to the note that got passed into this function right here. And if they're the same, so if the letter that got passed in matches one of the letters in the array, i.e. one of the notes, then we're going to grab the frequency stored in the frequency array at the exact same index, because again, I is going to pass into both. We're going to grab the frequency that corresponds with that note and assign it to current frequency. So basically we're going to say, yes, the current frequency is there, and we'll get it. So again, just to show you those arrays, we're going to be iterating through this array using the for loop. The first time index is 0, and then index is 1, and then index is 2, all the way up to index being 14, because there's 15 elements, but 14th would be the last index. And so when we're at index 0, and if we compare, if the note that got passed into the play function was C, we'd compare note sub index 0, which is this. Does that equal C? Well, yeah, it does. And then we're going to grab the element in the frequency array at that same index, index 0. And then we're going to call the tone function. So this is the tone function we talked about. And again, the things that you pass into the tone function, the first, it's 3 arguments in this case, but the third argument is optional. You can just pass in 2. The first argument you pass in is the pin that the buzzer is connected to, as you can see here. The second argument is the frequency that you wish, so pass as frequency, converted to a non-sign int, the frequency that we find when we look up frequencies array. So this is the frequency that you want to send out to the pin, whatever frequency that is, which we have down here. So C is 131 hertz and so forth. And then the third is optional. This is the duration that you want to play the frequency for. So this would be beats times beat length. So beats, where did I have beat lengths? We have right here. So beat length is 150. We've already declared that as a local variable to the play function. And then so we're just going to go beats times beat lengths, and that way 150 times whatever the beat happens to be, and that will be the duration that we play for. And then because that's happening, but the Arduino code will keep going on, we also have to delay the code for that same length of time. So again, we're delaying for the same length of time, beats times beat length, basically waiting for the length of the tone so that it has time to play. Because just because we call the tone function and say do that, as soon as the code goes on, it'll just stop whatever's happening. So we have to delay as well. And then we've got this extra little 50 millisecond delay just between notes to make this song sound more natural. And this is just a multi-line comment, just showing the chart of frequencies for notes in C major. Again, I'm not a music aficionado or anything like that, so this is all Greek to me, but that's the frequencies associated with the different things. And so that's fairly simple code. We're going to upload that to our program. COM11, and then we'll go to the board. So we can see the code works, and I can adjust the volume using the potentiometer here. So again, the code is designed only to run once. As we can see here, we ran the code, we play through once, and then we enter this while loop, which is just a forever loop. So it does stop. I'm going to temporarily comment that out so that we'll play again and again, and you'll be able to hear the volume change as I adjust the potentiometer. So I've got the volume all the way down, and I'm increasing it. So that's all the way up, and this is all the way down. So you can see you can barely hear it when it's all the way down, and then as I turn it up. So we've set up the thing, we've got the program working, the first circuit working, where it's just going to play, in this case, Happy Birthday over and over forever, because I took out that forever while loop, and I can control the volume with the potentiometer. And I think we'll add that while loop back just to get rid of that forever song. And as usual, I've obviously got a lot of circuitry on here when really all I needed was the speaker and this potentiometer. But again, I'm relying on you guys looking at the schematics of the SparkFun guide, and I'm just going through showing you basically a fellow student doing the code. So that's that circuit. But now we're going to jump to another circuit. So I did the challenge for this, and we're just going to open this up. Actually, I'll leave it just like that. So I did the code challenge for this, and as usual, I've done Doxygen comments. Doxygen comments are basically by adding this extra asterisk. You can see the color change on these tags. By adding this extra asterisk, I basically set up so that I can run this code through an external program like Doxygen and basically create some really nice professional looking HTML documentation associated with this program. And that's why there's 3 forward slashes as opposed to 2. This is just a regular inline comment associated with Arduino, which is based on C and C++ commenting, and this allows the Doxygen comment. This basically just tells the Doxygen program or similar program to do something special with these comments. So, but anyway, that's enough about the commenting. So basically, this code's not too much different. I still have my speaker pin. I did make it a constant by putting the keyword constant in front of the variable declaration. And by convention, I made the name uppercase, separating individual words with an underscore. However, this is not necessary. This doesn't change anything from when it was an int before, and this was lowercase. This is just a convention I've done. I've also had a pin so I do have something commented out here. We'll go to that in a second. Again, this is just the length of 1 beat in millisecond modified to change the tempo. So this is the exact same value the beat length was before, 150 milliseconds. The total number of notes in the note and frequency array. So when I did this up, I did 15 because I counted them. And as I was saying before, I think there was an issue. I think it should have been 15. So I've put 15 here and it seems to work. But again, I've made this a constant because I'm not expecting anyone to change the number of notes of these things. So I made it a constant, and thereby, by convention, I've named it all with uppercase letters, separating words with an underscore. Just spread this out a little bit. Let's just make that big for now. I've got 2 arrays here, same as before. I have my note array of type char, so my one-dimensional array of notes. So it's an array of type char, and it's constant. I don't know if the other one in the code is constant, but I made this constant just to indicate that these aren't going to change. And I did the same thing for frequencies. It's one-dimensional array of type int, and it's constant. And I've named them uppercase letters because I've made them constant. I also included the size in the array. This is not actually necessary. You need to do this if I was just to declare this. Like if I was just declaring the array and then going to initialize the values later, I would have to indicate the size of the array. But if I'm initializing with a list right away, Arduino and most programming languages, C and C++, actually determine the size based on the number of elements. So this is not actually necessary. So you can do it, but you can also just do it like that. You don't actually need to specify the size. So I'll leave the size in here just to show that either one is fine. But again, this is the same as before. The note matches up with the frequency. The corresponding note matches up with the corresponding frequency. And then I've got some notes because, again, the whole point of this coding challenge was to have individual songs. Oh, you know what? I've just realized, I apologize. I've already let this video get away from me because I've already let this video get away from me because I haven't even showed you the coding challenge. So before I go into that code, let me go over the code to note associated with just the original circuit before we get to the coding challenge. Again, we dealt with some character variables this time. So with the keyword char, the char or character variable stores character values. That's what our notes were. So C, D, E, F, G, A, B, that sort of thing. The tone function, again, that's our bread and butter of this project because we're dealing with sound. And again, it takes in 3 arguments. It takes in 2 arguments for sure, and a third argument optional. So the tone function will pulse power to a pin that we specified, the buzzer pin, and you will pass in at a specific frequency. So again, you need to pass in the pin as the first argument, the frequency that you want to pulse to that specific pin, and the duration controls how long the sound will play. But again, that's optional. If you don't do it, you just have to call the no tone function afterwards. And again, the tone function can be called on any digital pin, which is funny because the tone function sort of works like PWM, Pulse Width Modulation, in a way, but Pulse Width Modulation can only be done on PWM pins, namely 3, 5, 6, 9, 10, and 11, whereas the tone function can play on any digital pin. We've also discussed arrays in this code and how to access arrays, and basically when you declare an array, you need to give it a size. So to declare an array, you must give it a name, then either tell the Arduino how many positions or assign a list of values. So this is the either. When you declare an array, you either need to tell the Arduino how many positions, like 15, or assign it a list of values. You don't have to do both, which is why I was showing you here that I have this explicitly telling you the size and then assigning values to it, but I don't need to do both. I either need to just declare the array and not assign these, in which case I would have to give the size, or if I assign values, I don't have to explicitly tell you the size. The programming language will understand and pull that. And an array must contain all the same type of variables and be declared as such. So again, that just means that I have, for example, this is a char or char array. So an array where all the elements are of type char. They're all character values. And this is an int. All the values in this array are of type int. You can't have an array where some of the elements are int, some are booleans, some are chars. You just can't do that. They all have to be the same. Calling the array, you use the array name, and then within square brackets, you give the index number. So we've seen that with the for loop, where we kept passing I to the array name, like notes array, note sub I, and frequency sub I, and I changed, but I under the hood was iterating through an integer. It was going to be 0 and 1 and 2. So you pass in an integer, or a variable representing an integer, into the array name inside these square brackets, and you'll access the individual elements. So you call one of the values in an array by using the name of the array and the index of the value. And again, we always start counting at 0. So that was going over the original code. And then I started to go right into my coding challenge, which I apologize for that. I'm a little out of sorts here. It is fairly late. I do a lot of my work after my kids are in bed, and I've done their homework with them. So, but enough excuses. So with coding challenges, I'm going to change the tempo of the song. I'm going to experiment with beat length, variable to change the tempo of the song. And then more importantly, what I liked is you can make your own song. Try changing the notes to make a different song. Like spaces can be used for rest in the song. But just make your own song with notes. I didn't actually do that because I'm not really music inclined. I could have just put notes in their CD and just made some jumble of music. But instead, I went online, Googled notes associated with, just certain songs that I just thought were universally known, certain melodies, and I put them in there, and I'll show you that. So let's jump to that. So, I already started going through this, so I won't continue. But as I said, it's with this code, for this coding challenge, we were going to introduce different songs besides the happy birthday they gave us. So I went online and just, looked up some songs, namely like, some Christmas songs, Deck the Halls, Merry Christmas, Jingle Bells, that sort of thing, and the Mario melody, because I used that in a previous coding challenge, so I already had the code, although it's in a little different format, because I did just pull it out of a previous coding challenge for Project 1, but I still made it work. But basically, these individual songs work the exact same way as our notes and frequency arrays do here. They basically match. We have the notes associated with a song, in this case, Jingle Bell notes, which are these notes, and the durations for those notes are this. And this is all, I just Googled to get these. There's lots of information out there, especially on GitHub, where people have actually done this a lot. So just grab that. But yeah, so I've just got char one-dimensional arrays for all the notes associated with the songs. So you can see all the notes are always char arrays or character one-dimensional arrays, and the durations are always int one-dimensional arrays. And again, the names just match, just notes versus durations. And again, the same number of elements will be in the int durations array as the notes array. So again, however many notes there are, there's that many beats or that many durations in that array. The Mario melody works a little different. If you watched any of my previous videos, you would have seen me use this in one of the coding challenges with a no touch button, I believe, using the photo resistor. So this one doesn't have chars in it, so I do have to treat it a little differently. I just pulled over the code that I used in the other one, so I just put this in because I like the Mario melody. And the durations are right here. And there's a little different way to calculate them, but we'll get to that. I also did, my kids have recently got into this show that's actually been off the air for 10 years, but they're really into it, Psych. And I like the theme song of Psych, so I tried to get that off of line 2, but it doesn't really sound that great. But anyway, do what you like, try to get your own song. There's lots of great information out there. But really, all we do in setup is I just, declared the speaker pin as an output, the same as we did before. I did add the serial monitor communication here, so by calling serialmonitor.begin with the baud rate of 9600, that's just so I think I could print the name of the song to the serial monitor. And again, all these Doxygen style comments with the /**, ending with an */ are just a special type of comment, so I can make some professional looking HTML code at one point. And these little tags just help the Doxygen program format these comments especially nice. In the loop, I basically, we'll get back to this here in a second. In the loop, we just play each song. So I call the play song function, which takes in 4 parameters. First one being a string representing the name of the song. Second one being a one-dimensional array representing the notes. This next being the one-dimensional array with the durations or the beat lengths, and then the size of the arrays. I just put Jingle Bell Notes array, but I could have put durations as well, because again the size of both these arrays are the same. And then I delay for 1000 between songs, and I think so right now I'm just going to play Jingle Bells and Merry Melody, but obviously you could play Psych or any of the any songs you put in there. I also did have a while loop in here as well, so I would stop playing just like the other code, so I don't play each song once and stop, but I've commented that out so for testing purposes. So here's the play song function that we've created. So I created this as a void function. It doesn't return anything, but it takes in 4 parameters, which you can read up here if you pause the video. Read the Doxygen notes and just realize the song name, again, is just a string representing the song. I'm just putting that on the serial monitor. The notes is just that array of characters representing the notes, durations, and then the size. So ultimately, I just pass that all in, and then I serial print the name of the song to the serial monitor, and then I use a for loop to iterate through the arrays. Now, that's the only reason I passed in this size function, is just so I could use a for loop and iterate the appropriate amount by using size here. If I didn't pass that in, I believe in the other code it uses a while loop. So the other code from, I'll just uncomment this, from the original circuit just passed in the notes as a char, as a pointer to char, so basically C-style string, and a one-dimensional array of type ints, and you didn't need the size passed in, and you didn't pass in a string because you weren't printing anything to the serial monitor. But the reason you didn't need to pass the size in is because they use a while loop. So they initialize a variable here, your loop control variable before the loop, and then they just do while some condition is true. They're iterating through the notes, in this case is a string, a C-style string, so which is an array, it's an array of chars, so they're just iterating through that array of chars, and they're checking, as long as it's not equal to the null character, they're going to keep doing this, and as soon as they get to the end of the string, they'll stop. So it's just using that condition and a while loop to iterate through the loop, and obviously we were loop control condition here. So they don't need to pass the size in, whereas I just used a for loop, so therefore I had to pass the size in. So that's why, yeah, I passed the size as a parameter. And then I passed this in just so I could print the name to the serial monitor of the song, but otherwise these are the two things that are the same as that other play song function. But ultimately when I go through the loop, however many times I go through, I'm just going to call the play function each time, passing in the 2 arguments to the play function being note sub I and duration sub I. So basically the note and the beat length of that note each time I go through the array. And we'll skip the play mirror for now. So what does that play function do? Again, we could read the Doxygen comment and realize that note is just the character representing the note, so the character, and beats is just the duration to play the note. So I pass in those 2 arguments, and I've got a lot of commented stuff out here. I was fiddling around, so just ignore any of the comment stuff and just focus on really this. This is really the main code so far. Out of all this is the code. I call the get frequency function, passing in note, so the note that I passed into the play function. I also pass into a get frequency function, and as the name of the function implies, that's a helper function that's going to grab the frequency for me associated with that note and assign it to this variable current frequency. So I'm just getting the frequency for the note. So once I do that, I come down and I say if the frequency is greater than 0, meaning it's not a break. If the frequency was 0, it would be a break and I don't do anything. But if it's not 0, meaning it's an actual frequency, I'm going to call the tone function, and again passing my speaker pin where the speaker is attached to, and the current frequency, whatever that was, that I got from the get frequency function and passed it to current frequency, and then play it for a certain duration. And again, I have to delay the code for that same duration. And then I think I originally didn't pass in this 3rd argument, so I call the no tone function, passing in the speaker pin. It just takes one argument, the pin that the speaker's on. But this is actually redundant in this case. I don't need to call no tone. I could even comment that out because I'm passing in this third optional argument to the tone function, which says play this frequency on this pin for this length of time. And then I use the delay function to ensure that the code pauses for that while I'm playing that on the speaker. So I actually don't need to call the no tone function in this case. So I'll just comment that out just to show you. In fact, maybe we'll leave it uncommented and then we'll comment it out and we'll see that there's no difference. Now, if the current frequency wasn't greater than 0, meaning it was 0, because there's no negative frequencies that we're giving, then we're just going to delay for beats times beat length. We're just going to rest in the song. We're not going to play any frequency, we're just going to rest for that length of time. And then we're going to delay between notes with 50 milliseconds, just to make it sound more natural. I've got a lot of things coming out. This was that other play function, the original one, that just took the 2 arguments, not the string, so that I could output to the serial monitor, and not the size, because I didn't need it. This is that get frequency helper method. Basically, it takes in an argument of type char, a character argument, and returns an int, the frequency. And it uses a for loop to iterate from 0 up to num notes, whatever the size of notes was, which was 15, I believe. And then I just basically check if note sub I equals note. So again, if the note that got passed into this argument equals the note at the index of the notes one-dimensional array, if that's true, then we're going to return the frequency associated with that same index. And again, that's really confusing, but basically, here's the 2 arrays again, notes and frequencies. And if the note that got passed in, let's say, is F, when my index is at 3, 0, 1, 2, 3, note sub 3 is going to match F, and then I'm going to return the frequency at index 3 in the frequency array. Where am I? So I passed that. So that's what I'm going to do there. Otherwise, I'm going to return 0. Basically, if I never find a match, I just return 0, indicating that the note was not found. And this is just a comment showing the notes again. So that's a lot of. It might be a little confusing the way I went through it. Hopefully not too bad though. And I skipped this. This is just the play Mario melody. This was in a previous video, so it kind of differs from the way I'm doing things with the other stuff. But I included it just so I didn't have to rearrange, so I didn't have to make the Mario melody match the same format of characters and different things. Because if I didn't include this Mario melody method that I had before, the code wouldn't work, because as you can see, Mario melodies isn't using chars. This is an array of int. This is a one-dimensional array of int, just like the durations are int. But all the other note arrays are chars. And this is an array of int because I'm using the pitches.h header file. This is just a common file that you can get off GitHub that have frequencies for all the common notes. So because I wanted to use this because I used it in a previous example and I didn't want to redo this, I had to pull over that same Mario melody function. But basically it does the same thing. It prints off the Mario Brothers theme song to the serial monitor. It uses a for loop to iterate through. I just have the hard-coded 16 in here because I know the notes array is 15 elements. So I'm just going to iterate through the notes of the melody. And in this particular case, this is something different that was explained, I think, before. But basically, my note duration is 1,000 divided by the duration that I pull from the array. So the durations are all like 12 or whatever. So I'm taking 1,000 divided by 12 in order to get my note duration, which is, I named it note duration, but because I just pulled this code over. But this note duration is the same as what I'm naming beat length everywhere else. So in all the other code, I call it beat length, and here it's note duration. And then if Mario melody sub I equals 0, meaning it's a rest, play the no tone. Otherwise, play that melody, that note, for that duration. on the speaker pin, and then delay for that same duration, because again, just because we call it on the tone, we actually have to delay the code for that. And then again, I called no tone speaker again. Not necessary considering I'm using this third optional argument. So there you go. With all that being said, as usual, this video is way longer than it should be, so let's just upload this code and see what happens. Let's just do this. On the right port, got the right board selected. Let's upload the code. So okay, so I'm just going to lower the volume there so it doesn't bother us. So that doesn't really sound like Jingle Bells like I had it before. I think I must have done some messing around with the code. But as you can see, when the song is playing, it does display on the serial monitor. So it plays Jingle Bells and the Merry Brothers theme song, and then it will just continue alternating between them because I did comment out. I commented out the endless while loop. But let's see what's going on, because that does not sound that good. So I think I must have edited the code in some way. Let's just make that, because that Jingle Bells doesn't really sound as good as I had it before. Let's try changing it to 100. Instead of a beat length of 150, we'll try 100 and see if that makes any difference. Make it a little faster. So yeah, that sounds a little better. I think we might even get it a little better with 75 or 50. Let's try 75. But again, this is you're just going to end up fiddling around with the beat length and the pitch and the frequency to get sounding the way you want it. So that sounds better to me. So I'll lower that volume. So yeah, that sounds better. So again, that's part of the anything with the sound projects is you're going to have to fiddle around with the beat length, the frequencies. Again, as I said, I tried to look and wasted more time than I should have trying to find the frequencies for the theme song for Psych because I liked it. And this could be it, but I mean, these are very short parts of it, and it just didn't sound at all good. So, you know, it's all something you have to play around with. You really like music and notes. I don't, so this wasn't the funnest project for me, but still important to see, and a lot of coding examples here. One other thing I did do is part of the coding challenge, it mentioned making a dynamic control for the beat length. So like I just had to change the beat length in code by changing it from 150 to 100 to 75 to get Jingle Bells to sound properly. But you could also I had some code here that you can see commented out where I'll just uncomment it and hopefully you can see it. I'll actually make this big again. So I'll uncomment this, but I basically added a potentiometer to the circuit, a separate potentiometer. Different than so this potentiometer here, different than the one that was on the original circuit, that I'm using to control the beat length. So I initially have it set to 75, that's fine, but I end up reading it in the loop. Let me just go down here. Yeah, so in the loop, I read the beat length by calling analog read on the potentiometer pin, which I'm using the map function to map it. So if you're not familiar with the map function, it takes in 5 arguments. The first argument is any value that is an integer value, and then the second 2 arguments are the minimum and maximum ranges of that value respectively. So I know that reading on the analog, when I do an analog read off of one of the analog pins on the Arduino, or the RedBoard in this case, it returns a value between 0 and 1023. So, and then the next 2 arguments, so argument 4 and 5, you pass in the new range. So basically now the 50 will be mapped, 0 will get mapped to 50, and 1023 will get mapped to 300. So basically what this says is, when I now twist the potentiometer knob from one extreme to the other, from 0 to 1023, it'll end up getting converted from a range of 50 at 0 to 300 at 1023. So now the maximum range I'm going to have is 50 to 300, and that's what I'm passing to beat length. I didn't have to map this. I could have just went from 0 to 1023 with the beat length, but I didn't think that sounded very well, whereas beat length of 50, that's pretty fast, but not ridiculous. And 300 is pretty long and doesn't sound anything like a song, but I just put it like that. So I use that. You can print the beat length to the screen just so we can see. And then I think I need it somewhere else. So actually this alone will work. Let me just try this and show you this code first. If I just do it once every loop, it will work, but there is a problem with that. Turn up the volume. So that's at a beat length of 50. You can see that here. 50 again. I don't know if you can actually see that, but it's 50. Because I have the potentiometer all the way to 0. And 50 gets mapped to 0, as we can see here. So that's pretty quick. But if I put the potentiometer all the way to the other end, which it didn't do anything that time. But now if we see, I've got the potentiometer, look, I've got it 300 here. And there's a huge beat length for Jingle Bells now. It doesn't even sound like Jingle Bells. But now I'm going to turn it back to 0. And you'll notice as I'm turning it, oh, I guess maybe you're not seeing it. I'm just saying you'll notice as I'm turning it, and I know you're not seeing it. So I'm all the way to 0 right now with the potentiometer. I apologize, I thought you guys were seeing that. So that's why I have a beat length of 50. And so that's pretty quick. Now I twist the potentiometer all the way to 300. But do you see how Jingle Bells was still fast? Now it's slow, so you can see I have 300 as my beat length now showing up in the serial monitor. Because again, 1023, I've got the potentiometer all the way to one end, 1023, which matches to 300. But you can see that if I change it in between, like look, I changed it all the way to 0 right now, but Jingle Bells was still slow for a minute. The reason being, and I'll turn the volume all the way down while I talk, the reason being is because I'm only changing beat length once. I'm calling it at the start of loop. So I'm reading I'm using analog read to read the potentiometer value and mapping it to beat length at the start of loop. But then I go into the song function, which has a lot of delays in it because it plays the song for however long that song is. And then I delay a second. I go into Mario function, play song, and then delay a second. So I only check the loop every, 5 seconds or so. Like however long 2 seconds for sure, based on these 2 delays, but also whatever time it takes me to play Jingle Bells and Mario Melody. So it's not really quick. Now there is something I could probably do with interrupts, which is a topic beyond this part of the project, so I won't mention it, and use like some time functionality. But really, an easy fix right now is just to read the analog pin more often. So I'm actually in the play song function now, and I'm going to read the analog pin because I know the play function is one of the bottlenecks because I go into play song, so I'll do another analog read. I'll also do an analog read inside Mario Melody. and again print it to the screen. So by adding those two other reads, I'll be able to change it more in real time. Not fully real time like I would if I was using interrupts or time functionality, but it will be faster. So I'm going to up the volume on this so you can hear the volume that Jingle Bells is playing with, and you'll see that I can change the tempo in real time. So let's up that volume, and let's, I guess, upload this new code. So I'm just uploading the code after I've made those adjustments and added functionality to have a pot pin. So I'm going to open the serial monitor too so you can see the reading of the pot pin is 25 right now, really low. So really quick tempo. And see how I changed to really slow tempo? We're like, what, 300 now? In real time, and I'll change it in real time back fast. So, fast, slow, fast, slow. And so keep it slow, and in real time change it fast, and then change it back slow. And Mario still went fast. So we see Jingle Bells is going slow. I'm just leaving it on slow for now. Slow tempo, 300. But Mario still went fast, I think. Let's just wait. Okay, I'm going to turn the volume down because Mario's still going fast for some reason. I'm not sure why that is. But nothing like live code demos. So beat length, I initially started at 75, but that doesn't really matter because I instantly change it when I read it in the loop. And this will read as whatever it happens to be. Right now it's 300. And then I recheck it both in play song and play Mario melody. So I reread it here, beat length, and then I reread it here. Oh, I see what the... Okay, so here's the issue. I'm rereading beat length, but I never use beat length here. So remember I said I brought over this Mario code from a previous coding challenge, and I was calling it note duration, which is beat length in this code. I'm using beat length in this code to control how long, to control how long I do things. So this is the actual in the code play, which is what play song calls, and I'm using beat length, which is why it affected Jingle Bells when I changed the beat length using the potentiometer, but it didn't affect Mario melody because everything is happening in here, and note duration is what it's using. So I'll just change the code here. I could either change note duration to beat length in both these spots, or just change this to note duration and keep the other two. You know, tomato sort of thing. But again, I could have changed note duration here and here to beat length and kept this, or in this case, I'm just going to change it here as to note duration. It doesn't really matter. And this should now cause everything to be affected, both Jingle Bells and Mario to be affected by the potentiometer affecting the tempo. So turn the volume up. And then we'll end this video because it's already an hour in. We've only got through one coding challenge. So see how slow that is? Hopefully that stays slow for Mario. I'll tell you when Mario starts playing because we'll see Mario theme come up on the serial monitor. Okay, and so that is a lot slower. It doesn't sound at all like Mario. So now we're going to adjust it back to fast, and we can do it in real time, so it'll come into play right away. And that's way too quick for Mario. Let's see, this might be good for Mario. It's not good for Jingle Bells, though. So, that tempo, 167, works good for Mario, not for Jingle Bells. This would take a little more fiddling to make it work for both, but that's not the point of this. It's just to show that you can dynamically use a potentiometer to dynamically control things, i.e. in this case tempo, as well as the volume. So a potentiometer can be used for a lot of things. So in both cases I'm using a potentiometer, in this case to control volume. So I'm not hooking into all three terminals, just the two. Using it as like a variable resistor. And in this case, I'm using it to, still as a variable resistor, but to read in a value between 1 and 0 and 1023, the ranges of the potentiometer, but then I then map it to a value between 50, or what, 25 and 30, 300, so that way for my tempo. So again, as usual, I apologize. It's a very long video to show a coding challenge, but I will still keep you guys on the line a little longer if you're still watching. Obviously you don't have to watch, but and I'll go through what I did, what the summary of this was. So here's I'll try to be a little quicker, and I'll unplug this get the sound of it. So the code challenge for circuit 2A. So what were the key things I did? I'll just kind of read the highlights. The key changes and improvements. I made it so you could do custom song capability, replace the hard-coded notes, which we had in the original circuit, with a function to read note sequences and duration. So that's where I could pass in the string of notes. And again, just download stuff online by looking up your favorite song, finding out the notes and durations associated with it, or just, type in some notes yourself and make some noise. Then I also created a get frequency function that allowed me to separate and improve some of the code. So that's where that get frequency function was where I called, let me see, where do I have it here? Get frequency right here. This was that little helper function I created so that I could just pass a note in and and then return the frequency associated with that note. So all the work to go through, to use a for loop to iterate through the notes array and compare every element of the notes array to the note, and then return the applicable frequency, I abstracted it away in that code so that here I could just call, I could just get the current frequency by calling get frequency note, whereas otherwise I would have had to put that code here. So basically I'm just using some functions, user-defined functions, in this case a helper function, to create some modular code. I also removed magic numbers by defining constants. I don't like magic numbers for the most part. I like to use constants, and I like to follow good programming convention by, not only do I like constants, creating constants for everything, speaker pin, potentiometer pin, that sort of thing, but if they are in fact constants where they're not going to change, I do like to use the const keyword and follow the convention of uppercase letters separated with underscores. But again, I try to use constants wherever I can. For the most part, it just makes the code more explicit, and you know what's happening. Like right now, I know I'm reading the potentiometer pin, and that's what's controlling my beat length or my tempo. If I just had, pin A0 in here, I don't know what that is. Is it a potentiometer pin? Is it a sensor? Whatever. So again, I like using constants. Correction, sorry. I was going ahead and reading ahead, showing that I added Doxygen style comments. So again, I do like Doxygen style comments. It's if anyone's familiar with C++ coding, which if you're doing Arduino, well, you are by virtue of Arduino is based on C and C++. Doxygen comments are great. And if you're familiar with Java, Doxygen comments are essentially Javadoc comments. Javadoc does the same thing Doxygen does. It just basically allows you to make comments that still work as comments in the program itself, but they allow you to generate really nice professional looking documentation, the type you'd find on Stack Overflow or in the documentation for C++ built-in libraries or Java libraries, that sort of thing. So I really like Doxygen style comments, and it doesn't take much more effort. I also made some scalable design. So basically I created that play song function that can handle songs of varying lengths. So that way it wasn't hard-coded that I was just going to go through notes which had like 15 elements or something. Improvements that could be made. You could change the beat length to adjust the tempo of the song. Either do it where I just changed it in code, or again implement a real-time tempo adjustment using potentiometer or button inputs. So I opted to do potentiometer, but again, you could do a button input where every time you press the button, you go up by 5 or 10 or whatever. Note sequences for popular songs that can be used in Arduino projects. I found these two websites really good. Arduino songs. I didn't go through all. I kind of played with more songs and didn't put them in this demo, but you can get like Doom and like just go through Jigglypuff song, if you're into that. A lot of cool stuff. Pac-Man. There's just a lot of good stuff in here that other people have already done for you. So why not? So also, and same with Arduino 4 projects. So same thing. A lot of stuff here. This tells you all about the tone function and what's going on. But yeah. So that's it. Again, thanks for coming and watching. If you stuck out this long, God bless you.